1. Introduction to Materials Science and Engineering. Materials science is the study and exploration of the interconnections between the structure, processing, properties, and performance of materials. Within this broad field lies metallurgy, a specialized branch concentrating on the traits of metals and alloys, including their extraction, processing, properties, and real-world applications. Materials are primarily classified into metals, ceramics, polymers, composites, and semiconductors, with a particular emphasis on metals, divided into ferrous and non-ferrous types. Materials can be analyzed at different structural levels, from atomic to microstructure, comprising grains and phases, to macrostructure, encompassing visible features. 2. Atomic structure and bonding. The atomic structure is made of protons, neutrons, and electrons, with electron configuration and valence electrons playing key roles in atom behavior. Materials are held together by different types of bonds. Metallic bonding involves a sea of delocalized valence electrons around positive metal ions, bestowing metals with high electrical and thermal conductivity, ductility, and luster. Other bond types include ionic and covalent bonding, which offer comparative insights into material behavior. 3. Crystallography. Crystallography delves into the ordered and repetitive atomic arrangement in crystalline solids. A unit cell represents the smallest repeating pattern in a crystal lattice. Common crystal structures in metals include face-centered cubic, FCC, body-centered cubic, BCC, and hexagonal close-packed, HCP. FCC structures, like those in aluminum, copper, and nickel, are close-packed and exhibit high ductility. BCC structures, found in alpha iron and chromium, are less dense and stronger, though less ductile. HCP structures, such as those in magnesium and zinc, have limited slip systems, rendering them more brittle. The coordination number indicates the number of nearest atomic neighbors, while the atomic packing factor, APF, measures the volume of atoms within the unit cell. The Miller indices provide a notation system for identifying crystallographic planes and directions. 4. Imperfections in solids. Crystal defects are imperfections within the lattice structures. Point effects involve localized disruptions, such as vacancies, missing atoms, interstitial atoms, and substitutional atoms, foreign atoms replacing host atoms. Line defects, or dislocations, are instrumental in material deformation, categorized as edge dislocations, extra half-plane of atoms, screw dislocations, spiral formation of atomic planes, and mixed dislocations, a blend of edge and screw. Surface defects encompass grain boundaries, which are interfaces between differently oriented crystallites, twin boundaries, mirror image grain boundaries, and stacking faults, irregularities in atomic plane sequences. 5. Diffusion. Diffusion refers to the movement of atoms within a material driven by concentration gradients. It occurs primarily through vacancy diffusion, where atoms move into vacant lattice sites,